Okay, welcome everybody and thank you for coming today. My name is Ricardo Vinuesa. I'm an associate professor at KTH in Stockholm. And today I would like to tell you a little bit about our recent work on using deep reinforcement learning to try to control turbulent flows and, well, hopefully try to achieve significant drag reductions and, if we are lucky, a more sustainable aviation in the future. This is work supported by the ERC, the European Research Council, and also some support from the VR, which is the Swedish Research Council. So let me start by giving a very short introduction to reinforcement learning. In reinforcement learning, you basically have a setup like this one, where an agent, in our case the neural network, is basically interacting with an environment, and the environment in our example will be a CFD setup, so a numerical simulation of a particular flow that we want to control. And then this interaction is done in different ways. The agent is essentially applying actions to the environment, and those actions are basically different types of control that can be applied. Then those actions will change the state of the environment, so this state will be updated, and at the same time the environment is also providing what is called a reward. And the reward is a measure of the quality of those actions under a particular norm. So in our case, if we want to reduce the drag, then the drag reduction will be basically the reward that the agent will get. And then through basically trial and error, the idea is to converge to a policy which will give us, given the state of the system, what is the optimal set of actions that will maximize the reward in the long term. So with this premise, we're going to try to devise novel strategies to control turbulent flows. We're going to be focusing on blowing and suction at the wall. So we're going to inject or remove momentum from the flow. And this is work led by Luca Guastoni, and this is published in the European Physics Journal E. This is the reference. Also, if you want more information about reinforcement learning, and in particular new developments that we are having for flow control, then you can check out the reference by Colin Vignon that you have at the bottom. So over here you have a very good and complete review of what reinforcement learning is heading towards in the context of flow control. So let me look at the setup. In the setup we have a turbulent channel. This is the lower wall. We're considering an open channel to simplify the dynamics of the large scales, which means that at the top we have a symmetry condition and we have periodic boundary conditions both in the stringwise and spanwise direction. So the flow goes in this direction over here. We're going to consider both a full channel and also a minimal channel. The idea to have a minimal channel, and I will talk more about it later, is to simplify the dynamics of the near wall flow so that hopefully we can control it more easily and learn something there that can be applicable to the full turbulence. We use DNS to basically simulate the open channel, and our baseline is going to be what is called opposition control, which was introduced by Choi and others. In opposition control, what you do is that you sense the near wall region. So basically this plane over here, that's typically at y plus 15. That's where the near wall peak happens. And what you want to do essentially with the opposition control is to apply a wall normal velocity at the wall. So this VW, which is given by this expression over here, in which we're going to sense the fluctuations in the wall normal direction on this plane, on the wall normal direction at y plus 15, and we want to cancel or try to cancel those fluctuations. So we have this negative alpha coefficient here, which what it's trying to do is when we have a vertical velocity in the near wall region, at the wall we want to have a negative velocity and vice versa. This is a bit of a simplistic model to try to attenuate the near wall fluctuations, but in fact it has led to quite promising results in many turbulent flows actually. So position control will be our baseline. So we will have as a reference the classical solution of the position control, and what we will try to do is try to devise through reinforcement learning something more sophisticated, something more nuanced to try to attenuate and kill those fluctuations than just trying to apply a velocity of the opposite side. This is the setup that we have. We are using what is called multi-agent reinforcement learning, or MARL. Essentially, we're going to divide our domain, which you have here, in those blocks that you can observe in this setup. Those blocks are going to be called pseudo environments, which means that each of those pseudo environments is going to be observing a part of the flow. Part of the flow would be this little blue section which is a rectangle in the near wall region at y plus 15, right above that region where the actuation is going to happen. And we're going to be sensing the state of the flow is going to be precisely the stringwise and the wall normal velocity fluctuations. Each of those pseudo environments are trying to, to find through trial and error the optimal sets of actions. The reward, as you can see here, is 1 minus the ratio of the wall shear stress divided by the uncontrolled wall shear stress. And then each of those pseudo environments are feeding into the same agent. So basically, each of those independent agents are sharing parameters in one big neural network. This agent is going to decide then the action, and the action is going to be applied at the wall, and that's basically a wall normal velocity. So a wall normal velocity that can be positive, that's blowing, or negative, which would be suction. So essentially, we have all these independent agents observing different parts of the flow. Because the flow is periodic in the stringwise and spanwise directions, we have what is called the invariance. So each of these pseudo environments can optimize, but then they work together collectively towards a common goal, which would be to minimize the overall drag. So this setup has led to very promising results in several configurations, and you're going to see that in the context of a turbulent channel, which, by the way, is at a friction Reynolds number of 180. So it's a low Reynolds number, but turbulent. So there is quite some potential here to do things, and we're going to see what we can actually do in the context of flow control. So here you can have a number of parameters that we decide in our actuation. So essentially we have a quite quick actuation, delta t plus is 0.06. So essentially we have less than a viscous time between actuations. So almost 2 actuations for each viscous time. The actuation is bound between minus u tau and plus u tau. So it's not a very, very strong actuation. You're going to see that if we allowed for a larger range of control magnitudes, we will have even more drag reduction. But even for this case, with a moderate actuation, we get quite some promising results. And we're using what is called the DDPG, the Deep Deterministic Policy Gradient, to be able to optimize our actuation. So you can see all the parameters here. I repeat and iterate that we have all the code open. So both the CFD part and the reinforcement learning part are open. You will see the link at the end of the video, so you can reproduce these results yourselves. And I really encourage you to try to have a look at the code and share with us your impressions when you use it. And now we're showing you the results. We are first using, as I mentioned, the minimal channel. The minimal channel is narrower and shorter than a full channel at arita 180. That means that the dynamics of the near wall streaks is simpler and easier to control. In this case, we can see actually the drag reduction as a function of time for particular episodes. And we can actually see in blue the drag reduction of the opposition control, and then in orange the drag reduction of the reinforcement learning. We can see that we are significantly outperforming the opposition control with over 40% drag reduction, which is extremely promising, extremely nice, even if this flow is slightly simpler. But perhaps the most interesting result comes when we take the policy that we learn in the minimal channel and we apply that to the full channel. So we basically take the dynamics of this policy that was slightly simplified, and now we go to a fully turbulent flow where the domain is large enough to capture all the streaks. So basically the dynamics is not simplified. And again, in blue we show the drag reduction of the opposition control, and in orange the drag reduction of the reinforcement learning. Now what we find here is that the drag reduction of opposition control is around 30%, which is good. But actually with reinforcement learning we can get much more drag reduction. So opposition control 20%, and then the DRL, the deep reinforcement learning, reaches actually 30% of drag reduction. So we get very, very promising results, a very high potential of application to more complex cases, to more difficult geometries, and in particular to try to see and learn something about the physics when we try to understand what this control is doing. And this is what we do next. We're going to apply quadrant analysis. So basically what we do is that we plot on the horizontal axis the stringwise velocity fluctuations, in the vertical axis the wall normal velocity fluctuations. At the top we see the uncontrolled case, in the middle the opposition control, and at the bottom the deep reinforcement learning case. What is interesting? If we look at the uncontrolled case, we see a predominance of Q2 and Q4 events. So basically the ejections and the sweeps, that's well known from wall-bounded turbulence. You have a predominance of these two types of Q events. And in the opposition control, what we see is that the control is trying to narrow down this oval that we can see at the top, but the physics is actually quite similar. We actually see still a predominance of Q2s and Q4s, perhaps a little bit less pronounced, but the flow control via opposition control is essentially very, very similar to the original, to the uncontrolled one. At the bottom, we see the DRL. And this is very interesting because you can see that the flow physically is fundamentally different from that present in the original and in the opposition control configuration. Now the predominance of Q2s and Q4s is gone. We have a much more even distribution among Q events. And in fact, what happens is that the streaks are significantly stabilized. The flow is not laminar. We have not relaminarized the flow, but we have been able to really significantly change the dominant flow features in such a way that this doesn't resemble anymore the typical quadrant analysis of a classical turbulent flow. And if we analyze the actuation, so here I'm plotting the velocity at the wall as a function of time. So the horizontal axis will be time. At the top, I'm showing you the opposition control, and at the bottom, the reinforcement learning. What is interesting is that the opposition control is eventually leading to lower and lower and lower actuation, because as the control goes by, the velocity fluctuations get smaller when the flow gets controlled. And the DRL is giving us some sort of two-step control, like a bang-bang control. We are saturating the maximum allowed actuation, which is plus minus u tau. We're going from very strong positive to very strong negative velocity actuations on the flow. And what we can see is that this type of behavior, which again resembles of the popular two-step control, is able to really have a significant impact on the physics of the near-wall flow. In fact, if we allowed a wider range of actuation, we would be able to have a more nuanced control physics, but even this approach is significantly more effective than opposition control, which is very encouraging, to try to understand a bit more what is happening. And perhaps it's also interesting to mention that scaling this to higher Reynolds numbers will give us a quite interesting wealth of physics when a multi-scale phenomenon, a much more pronounced multi-scale phenomenon, needs to be tackled with the reinforcement learning. So that's everything that I wanted to tell you today. I want to also highlight that there is a GitHub repository following this QR code where you can find the CFD part, so the simulation, all the reinforcement learning, the coupling, everything is open. Over there you will also find many other repositories for other machine learning applications that we have in our group. So feel free to use them, reach out to us to discuss, and we're happy always to collaborate and try to find new exciting applications of machine learning to fluid mechanics. And I'd like to thank everybody who made this possible. I would like to thank InfraVis, the KTH Visualization Studio, and the KTH Digitalization Platform who really enable these videos and this content. And of course, if you're interested in more of this, just feel free to reach out. And we'll be very happy to share more on turbulence, fluid mechanics, and also machine learning. Thank you very much.